All right, so today we're doing the 4.4 notes. 4.4 and 4.5 worksheets go together. This is related rates, and this is a pretty tough subject. Related rates is dealing with two different things changing at the same time. Like maybe you have a square or a rectangle where the length and width are growing, or circles that are expanding, or maybe you've got volumes where a height's increasing while the volume's increasing. So these are pretty tough problems, so you're going to want to make sure you listen to this and take good notes. So we're going to talk about water being poured at a steady rate. So the rate the water is going in is constant, doesn't change, into these containers. So as you're pouring water into the top of this thing, this water is raising, and the height's raising, which is this height. It's going up as time is passing. The water level is going up. And since this thing is exactly uniform, there's no changes in design, this kind of deal, the height and the time, it should be just a straight line. I could draw a straight line. That's what that related the time and the height would be, because it goes up. Now, if you got a bigger base down here, it's kind of like this, starting as you're coming in here in this area and you're filling this up with water. Okay. This would be constant, but it's kind of going to be slow because it's so wide. So it'd be some kind of a straight line coming out here. And then when it gets up to this point, then the rate of the water going in has not changed, but the amount of volume coming in here is changing. So it's going to start increasing at a faster rate at the top part, because you got less volume going in here with the water going in the same as it was at the bottom. So this one is going to have three different changes. So again, just like this one, the first two things are the same. It kind of starts off slow, and then it goes faster, and then it goes slower again, because the amount of volume is big, smaller, bigger. And then this one is kind of the opposite, because the volume of this is small, and then it gets bigger. So when it's small, it's faster, and then when it gets bigger, it goes a little slower. So hopefully you can see how, as time's changing and the height of the water's changing, it's going to change what the object's going to be doing. Now, some of the key things about this is we're going to be talking about rates of change. The rate of 3 inches, and if you notice, this is inches per year, which is a rate, which is a derivative. And since we're talking about somebody growing, we're going to call that probably height. So that means the change in height, dH, with respect to t years, because inches is height, years is time. So I'm going to put h for height, time on there is going to be 3 inches per year. If I look at this one, we're talking shrinking. So we are getting smaller on this one. So when we do this one, mutual fund, and we're talking money, right, cents, and this is a mutual fund in cents, so I don't really know what we call it. I'm going to use F for the change in the mutual fund. And again, this is time, so this is going to be DT, days or time. And since this says shrinking, this is going to be negative. Now you notice this says cents, so we need to put a 0.4 in here, and we would call that cents per day. Coming over here to this one, the radius is what's increasing at 4 feet per day. And radius in feet, we're talking length, but I would call, since it's a radius changing, I would say the change in the radius with respect to time, and because hours is time, and increasing makes that 4 positive, would be 4 feet per hour. And then we're going to be changing volume, and it's decreasing, so we're going to have a negative one, so dV. And again, seconds. And another thing that's going to help you know it's volume, do you notice that says cube? So that's a volume symbol. So dV dt here, and it's going to be decreasing, so that would be -2 cubic inches per second. So that's kind of giving you an idea of what we're going to be looking at with derivatives. So in this part, we're going to draw a picture, and you're going to want to draw pictures on all of these, and then you're going to state all the things you're given, and then what you're looking for, and what you're looking for, and then down here we're going to come up with an overall equation. and then we're going to talk about what we do to solve this thing. So a rectangle, so as soon as I read a rectangle, I'm going to stick a rectangle up here. And it says a rectangle's length is increasing and its width is increasing. How fast, and again, fast is another word for rate, is the perimeter changing the moment the length is 10 and whatever. So when you draw a picture here, don't put numbers on this picture because these things are changing. This is getting bigger this way, and this is getting bigger this way. So we don't put numbers on this except if they are constant the entire time, but everything's changing here. So we're going to label that L for length, and we're going to call that W. So we're going to be doing this thing. Now this says the length is increasing at a rate of 2 inches per second. So that's one of the given things. So the rate of change of the length with respect to time is going to equal 2 inches per second. And the width is increasing at a rate. So that's going to be dW dt is going to be increasing at 3 inches per second. Okay, what are we looking for? This says how fast is the perimeter changing? So perimeter, we're going to put dP for perimeter. What's the rate of the perimeter change per second? That's the thing we're looking for. And then we want to find this answer. When do we want to find this answer? At the exact time L equals 10 and W equals 6. So what's the equation for perimeter of a rectangle? So we're going to put P equals 2L plus 2W. So now we've got to get all these symbols in here. So we're going to do the derivative of this thing with respect to time. Okay, because all my bottom things are time. So when I do the derivative of P with respect to time, that would be 1 dP dt is going to equal, leave your 2 in front, and then the derivative of L is dL dt, and then the derivative of 2W, leave the 2 in front, and that would be dW dt. And then we take and plug all these things in where we know them. So we're going to take this thing right here and plug this dL dt. And we're going to plug in this dW dt. And then that would be the answer. Now you probably ought to solve this. This is 4 plus 6. This is going to end up being 10 inches per second. So when we answer this, you'd write down the rate of change in the perimeter is 10 inches per second when L equals 10 inches, the length is 10 inches, and W, or the width, equals 6 inches. So we would actually write that out in words, but I don't have room, so I'm not going to write that out. Now it says the rectangle's length is increasing by 3 inches, so we're going to do dL dt again, is going to be 3 inches per second. Now the width is decreasing, so now dW dt is going to be negative 2 inches per second. And I should have drawn a picture, and I did not. I'm sorry, but it's the same picture as above. We got a W and we got an L. Okay, and now it says how fast is the area changing the moment the length is 10. So we're looking for dA dt. You want to know what that is when L is 10 and W is 6. Okay, so our equation for area is going to be length times width. That's the area of a rectangle. So now we have to do product rule. And again, this is going to be a derivative with respect to t. So we got to have all the derivatives are not with respect to the same variable. So the derivative of area is dA dt. And now we got to do product rule over here. So we take first derivative of the second plus the second times derivative of the first. And now we got to plug our numbers in. So dA dt, which is what we're looking for, is going to equal, well, we're looking for L when L is 10 inches. So this is 10. There's inches there. Times dW dt. So that's going to be negative 2 inches per second. And I hope you see that inches times inches is inches squared because it's an area. And then plus 6 inches, W is 6 inches, and dl dt is 3 inches per second squared. So see, this is going to be negative 20 inches squared per second plus 18 inches squared per second, which is going to end up being negative 2 inches squared per second. So when we write the answer to this, we would say the area is changing at a rate of negative 2 inches per second when the length equals 10 inches and the width equals 6 inches. And some people might want to write the word decreasing, but if you put decreasing in negative, that will be wrong because that'd be a positive. Okay, next problem, example 4. It says find the rate of change of the area of a triangle. So now we have a triangle on this one. So let's see what it says here. It says a right triangle, so I'm going to draw a right triangle over here. Try to draw a right triangle over here. Find the rate of change of the area. So we're finding the rate of change of the area. So what we're finding is dA dt again. At the moment, the short side, so we're going to call the short side A. So I'm going to put an A here. The minute the short side is 30 inches and the long side is 40 inches. So we'll call the long side B. B. Okay, so we kind of got a little problem. Oh, I didn't read this up here. So it says a right triangle has a short side increasing. So I said I'm going to let A be the short side. So dA dt is increasing at 3 inches per second. And dB dt, the long side is decreasing, so that's a negative 5 inches per second. An equation of a triangle is area equals 1/2 base times height. And I'm letting base and height be A and B. If you did B and H, that's fine, but you got to make sure you tell which is the longer side. So I'm using these. So I'm going to do product rule again here. So the derivative of A with respect to time is dA dt is going to equal, and then we're just going to leave the half in front. And I'm going to do just, or I could say that's a half A, but I'm going to put the half in front, just leave that coefficient in front and do product rule just A and B. So first term, derivative of the second term, plus the second term, derivative of the first term. And then I'm going to plug in all my values. So got that half in front. A is 30, and that's 30 inches, by the way, 30 inches. So I'm going to go ahead and put inches there. And then dB dt is negative 5 inches per second. And then we're going to go plus B. B is 40. And dA dt is 3 inches per second. And we go ahead and solve this. So that'd be negative 150 and positive 120. So that'd be negative 30. And half a negative 30 would be negative 15 inches squared, because inches times inches is inches squared per second. So we would say again, the rate of change of the area is the rate of change of the area is negative 15 inches squared per second when A is 30 and B is 40, or you could say when the short side is 30 and the long side is 40 of a right triangle. All right, we got this part says how fast is the hypotenuse changing at the moment. So now we're looking for the rate of change of the hypotenuse. So all this stuff up here is the same. So just to save time, I'm not going to write this down, but we're using this same information right here, right down here. But now we got a triangle, and we're worried about the hypotenuse. So this is A, this is B, this is C, and we are wanting to find dC dt. That's what we're looking for, and I should have put a question mark there. And again, when A is 30 and B is 40. So all that stuff's the same. But now the way these three things relate in an equilateral triangle, It's a squared plus b squared equals c squared. But I'm going to put the c squared on this side. So now I want to do Pythagorean theorem, which is where that came from. So I'm going to do the derivative of c squared. So we do 2 comes in front, c stays there, but we're doing the derivative with respect to time. And the 2 goes in front of the a, and we're doing the derivative with respect to time. And the 2 goes in front of the b, and we're doing the derivative with respect to time. Now, I would probably divide everything by 2. You don't have to. You can leave the 2 there and divide later, but if we divide everything by 2, it's going to simplify this a little bit. And then we're going to plug our stuff in. Well, we got a little bit of a problem here. We got a is 30, and again, that's inches, and dA dt is 3 inches. And I'm getting low on time here, so I'm not going to label these, but you're going to have to label it at the end. And we got 40 for b, and dB dt is -5 still. And over here, we're looking for dC dt. But we've got an extra variable here. So we got to be able to find that. So we actually use Pythagorean theorem here. So c squared, we want to know that when this is 30 and when this is 40. And when you do Pythagorean theorem, you're going to get c is 50 inches. So we get to stick 50 in for this. And so we're going to now solve for this thing. So let's see, this is 90 minus 200. I believe that's -110, if I'm not mistaken. And over here, I got 50 dC dt. And you're going to divide by 50, so I believe dC dt is changing at a rate of -11 inches per second. Now, this is going to be inches because this thing over here, this 50 is in inches. And this over here is inches squared per second, just like it was up here. But because that's 50 inches, when you put that 50 down here, you had an inches squared and an inches here. So this inch reduces with one of these, and that would be -11 inches per second. And c's a side, so you're not going to have a square there. Okay, I've got one more problem to do, and I'm kind of in a bind here because I got another class getting ready to start, but we're going to do this as quickly as I can. A right cylinder, so we got a cylinder over here. Looks like this. And this is a radius, and this is the height. And let's see, the radius is growing at 2 feet per second, so dr dt equals 2, and that's feet per second. And the height is shrinking, so dH dt is going to be -3 feet per, I said second, it's minutes. I didn't read the label up there very well, so be careful not to do that. You can lose a point if you change them. Find the rate of change of the volume. So we're looking for dV dt. We want to know that when the height is 10 feet and the radius is 8 feet. So the volume of a cylinder, hopefully you guys remember this. So the volume of a cylinder is going to be pi r squared h. Now pi is a constant. So when we do the derivative of this, we're going to have dV dt. And I'm just going to leave that pi in the front, and then I'm going to do product rule with r squared and h. So first term, derivative of the second term, plus the second term, derivative of the first term. Now that's going to be 2 comes in front with the r and dr dt. So there's my derivative. And again, I'm running out of time, so you got to plug 10 in for the h, you got to plug 8 in for r, you got to plug these numbers in for those variables. And I'm going to let you finish that out. And dV dt here should end up being 128 pi. Now we're talking volumes, so you're going to have, this is feet squared when you plug that in, and that's feet. I hope you all know that's going to end up being feet cubed. And it's going to be feet over here because that's feet times feet times feet. That's feet cubed, and it's per minute. So see if you get that answer when you plug those in. Last problem, we still have a cylinder here. This is still a cylinder, and this, let's see, the radius is decreasing. So dr dt is decreasing, so that's -4 feet per second, or minute, not second. The height is increasing, so dH dt is 2 feet per minute. Find the rate of change of surface area. So we are looking for ds dt, I'm going to call that surface area, when h is 10 feet and r is 8 feet. Now we have to know the surface area for a cylinder. So the surface area of a cylinder are the two bases that are circles. So pi r squared is a circle, and there's two bases, top and bottom, so that's where 2 pi r comes from. And then the lateral area, if you don't remember from the good old days, is this 2 pi r h. Okay, so we got to do the derivative of this. So we get dA dt is going to equal, now 2 pi is a constant, so I take the 2 times 2 pi, that's going to be 4 pi r, and then dr dt, plus, again, 2 pi is the constant, so I'm going to put 2 pi in here, and then I'm going to do product rule with r times h. So it's first term, derivative of the second term, plus the second term, times derivative of the first term. And then I got to plug all of this information, all these numbers, these 4 numbers have to go in over here. So you're going to have to plug all those numbers in, and when you get done with this, you're going to get -176 pi. Notice we're leaving pi, so don't put pi in your calculator. Feet squared, because we're talking area per minute. So check that out and see if you can get that answer. Have a good day, and I will talk to you next time.